Alrighty, let's get started here. This is Game Engines, and today, because we're doing this virtual class thing, I thought I'd talk about a little bit of a change of subjects. We're going to talk about the game development process overall, and this is something that we needed to talk about this semester anyway, so it makes a lot of sense to talk about it today while we're having class off-site. I don't know what the heck happened to my... Oh, there we go. So we're going to talk about teams and processes, various languages that are used for the game development process. We're using blueprints for game engines, but I don't want to give you the idea that that's all that's used in the industry, so I want to talk a little bit about what other languages are used and popular. Talk about debugging, which is very important, and this miscellaneous stuff we probably won't get to today, but maybe we'll talk about that when we reconvene next week. Um, So it used to be back in the day that programmers were all that was needed to create a game. Art was, you know, boxy pixel art. Um, Over the years, this shifted, and we ended up getting game content creators such as artists and designers in. Um, you can think of the programmer as basically the glue that puts everything together, as like sort of a service for, well, you've got your art team and they create the 3D models and the animations and things like that, but then someone's got to actually put it in. That's what the programmers do. But really, ultimately, without the programmers, there wouldn't really be a game. There's various parts of game code that we like to talk about. How the camera behaves, the AI. Um, Also, programmers and designers quite often use scripting languages. And we'll talk about scripting languages, and that's like visual scripting like you're using in UE4. That can be used by programmers, but it can also be used by designers. So, for example, it can allow our technical designers or our artists to actually change behaviors and modify game code. Um, the the game engine itself, when you think about UE4, for example, it's support code that draws the graphics to the screen that enables us to um, isolate the code from the hardware. So things like controllers, graphics. That way we can just focus on what makes a great game. So there's various programming tools that you're going to get used to, like you're getting used to the level editors, the particle editors, all that stuff. Um, there's some that are scripting related, like bash files that you run that usually don't have any GUI. There's off-the-shelf tools like Maya and 3D Studio Max that are used for building content. It's also true that this is something important for you to know for the class. There's specialties of game programming. There's graphics, networking, AI. There are generalists that know a little bit about everything, and they tend to be sort of good for lead programming roles. Um, in a traditional game team, you're going to have more than 10 programmers, probably with several leads, and sort of a full-featured team. We should talk a little bit about software methodologies in this class because it's so important to game development. These are ones that are used: code and fix, waterfall, iterative, and agile. Agile is probably the most popular one these days, and a lot of this is overlap content from software engineering class. Code and fix is an all too common method where basically you just get stuff in there and you make it work. It's all reactive. It's like, okay, if there's bugs, we fix them, and we just want to get to a rate where we're fixing the bugs faster than they're popping up. It really produces crazy amounts of crunch time. Um, Results in burnout because you're always working on something. You're always trying to cram in more fixes. Waterfall is where we actually plan ahead of time for the game, and basically we have various steps that we have to do, such as requirements analysis of the game, design, implementation of the game, testing of the game. Again, this is I'm covering this now because it's very important for game development, but we get into this in great detail in the software engineering class. Um, it should be said that waterfall is typically very brittle, and it's not great for game development because what can happen is during the course of developing the game, you can decide that certain things are more important than others based on what's proving to be fun, what's proving to be a success in the game. So waterfall is a very hard method to use in game development. Um, a slightly more modern approach is iterative, where we work for a period of time on a subset of features for the game, and we refine those and make sure they're working. And in iterative, you can sort of cycle around one set of features, get it in, try to get it to work, fix it, then take the next set of features, and over a period of time, you get the game working as a whole. Now, by far the most popular one that's used is Agile. Agile basically comes in with an approach of saying, look, things are going to change in the game development process. We're going to decide that, for example, it's not fun to, I don't know, do a double jump. It's not fun to be surrounded by a bunch of enemies and die right away by one-shot kills and things like that. That is where Agile really comes in because it allows you to balance the fun and scale and add new features as are needed to really get to that level of enjoyment that the players need. So that's become the dominant way of doing game development. So I wanted to take a minute to talk about common practices that we use in game development, um, because as I said, prior to this course has been mostly about, well, how do you do stuff in UE4, and that's not the full story. And sort of you had your midterm, and from here on out, we're going to explore things that are surrounding game development, such as the game development process, as well as some more theory behind the game engines themselves. So it's going to take a little bit of a different approach from here on out. I haven't updated the syllabus with some of that stuff, but most of it's in there. One of those things that needs to be talked about is version control. So this is another software engineering topic, but basically it's a database containing all the files that are in the game, all the C++ files or blueprint files or what have you, and a past history as well of what has been changed on those files. This way, if you have an error in the game, you can backtrack and see when the last time is that it was actually working. So version control is very good for. I even recommend version control for personal projects. You can go and you can get perforce, for example. So we've got, if we talk about various types, we've got perforce, we've got team foundation server, we've got GitHub and Git in general. We've got SVN. You've got a bunch of different types that allow for you to do this sort of database of past files, and it's very important. Mostly, if you go into an interview at whether it's a game interview job or a traditional software development job, they're going to want you to have some amount of knowledge about version control. So it's very important. Obviously, if you're in the software engineering track here at GB, you're going to be taking software engineering, and we'll talk about it there. But if you're not and you still plan on getting into programming, this is something you'll want to discover on your own. Perforce, GitHub, that kind of thing, and just how to use them. And we'll talk more about that in that software engineering class I mentioned. Another common practice on game programming teams is code reviews. So here is where, so you've been operating sort of in a vacuum. I mean, I give you these little assignments and you do them. Really, what usually happens is before you're allowed to commit, before you're allowed to check in your change, in other words, before you're allowed to put it into the database, you talk to another programmer and you review the changes you've made. So this is called code reviews. Code reviews are a common practice not only in game programming but across the industry. Other common practices are the usage of asserts. So instead of doing a hard crash, we can force the program to crash. Things like null pointer checks. Obviously, these are removed during release, but during the development of the game, and you've got your testers playing the game, it's useful. Excuse me. It's useful to have asserts because you can have your testers reporting back to you that they were doing a certain thing in a certain part of the game. They got an assert and they got a certain message. It allows you to debug, which is what we're going to look at in a couple slides here. Unit tests would be things like testing for physics computations and other things. That's a very important part as well. Acceptance testing is where we see if a level is loading correctly, and if it does load correctly, we say that that feature is done. The bug database itself is, for example, like a Jira or a Bugzilla. These are bug databases, and these are things too that, again, in interviews this might come up. Bugzilla, Jira, Fogbugs. There's a bunch of others. Axosoft. These are just basically bug databases, and what happens is the testers are testing the game as it's being developed, and as it's being developed, bugs come up. They put them in the bug database. Then the producer, because the games industry is weird, it doesn't like the term manager, but basically a producer is a manager. That person decides which bugs are going to be fixed and which bugs aren't going to be fixed. So this is back to the outline. So moving now over to languages, programming languages, I wanted to give you a little sample of the world outside of visual scripting, because even though visual scripting is great, like we do with blueprints, it is certainly not all that you need to be a game programmer. C++ is still the dominant language in most of game programming. Compilers are fast for C++ because they're based on C. They're very performant, meaning that you can really optimize C++ code. It maps closely to the hardware, so like drivers and video drivers, things like that. You know what the instructions are going to be. Memory management is controlled by you, so the programmer, so you don't have to be guessing when garbage collection is going to occur. These are all reasons why C++ is chosen. Game programmers tend to want the ultimate amount of control over their code so they can really optimize it. In C++, it also allows us to have high-level things like classes, polymorphism, templates. There's a wealth of libraries available in C++, such as OpenGL, DirectX, also containers like vectors and algorithms from the standard template library. Now, this STL is actually often replaced with a custom version. When I was at Raven Software, we worked on a custom version of STL. So I'm going to say STL is often too slow, and a lot of companies roll their own STL-like library. All that the STL is a standard template library, so it allows you to have things like vectors and lists and maps and hash tables and things like that. A lot of companies choose to have their own to save on memory and that kind of thing. There's still some issues with C++. It's very complicated compared to other languages like Java. Lacks a few features that didn't exist at the time C++ was made, like serialization. You have to use external libraries for that. slow iteration time. It's hard to sort of improve on the code very quickly. For that reason, some people have been going over to Java. These, although it still hasn't really caught on, the C# is really what's caught on more in scripting languages. So what's happened a lot is now that scripting languages are important, such as I would say the ones here that we're going to talk about that are important are C# for Unity and Visual Blueprints for UE4. This allows you to sort of, you develop your engine in C++. So your engine is C++, and then your scripting goes on over here. So you've got your C++ over here, and you've got your scripting over here. So, designers, programmers, mostly programmers these days, well, sometimes designers and tech designers, can work all in this area, and your engine programmers can work over here in the C++ area. It allows for less technical knowledge of the engine, and we can iterate more quickly in this scripting system. We can sort of make a change and test it, make a change, test it very quickly. So most scripting code is parsed and executed on the fly. That means it's a little less efficient. They have some ways of dealing with that to turn into bytecode and things like that. Other scripting languages that have become prominent are Python, Lua, Ruby, JavaScript, GML, Unreal Script, obviously, which has now given way to Blueprints. Some of this stuff is from older, obviously older information, but Python is still very popular. Lua is popular. These are all scripting languages, again, that plug into that same approach that I talked about before, where you've essentially got the C++ engine here. You've got your C++ engine, which is where our engine programmers reside. And then you've got your scripting, which is where your game programmers reside. So this is our engine programmers. And they're down there working on, like the physics processing, the rendering. Meanwhile, up here, your game programmers are working on more of like the level logic and that kind of thing to actually pull the game together and make sure that you can open a door with a key and that kind of stuff. All right, so the last section to talk about today is debugging. These slides are from WPI, and which has a book out on game development, and that's what these slides are from. This is from chapter 3.5 in the Introduction to Game Development book, and that's where these slides are from. But I thought this was a really interesting section, so I kept it because a lot of times, with debugging, we sort of assume that you're going to figure it out on the fly, but it can be very hard the first time you start getting used to debugging, and it's very important for game development. So there's steps involved here, and I want to go over those steps. The first thing when you've got a bug is you want to reproduce the problem consistently. Find where it occurs. Like for example, if you get a report saying sometimes the game crashes after you killing the boss, that doesn't help that much. You want to identify that bug, start it, go to the map, find the camp, use whatever, have a systematic way of reproducing this. And this gets into good testing methodologies. A good tester will do parts of this for you. They'll reproduce the bug for you. Your QA department will reproduce it for you. That doesn't mean you don't have to do it eventually when you get to fixing the bug. You do still have to reproduce it, but hopefully they've at least given you the steps to reproduce it. Now you get into the phase of actually needing to fix the bug. So you're collecting clues here. Like you're thinking, well, what, for example, if it crashed using projectile, what about that code would make it possible to crash? Was there a null pointer reference? Was there some corrupt memory? Was a certain parameter not passed? What are the problematic issues of using a projectile? What are the methods that are used in using that projectile, and how might that cause a crash? Here, it's sort of like brainstorming. You don't spend a ton of time. You just get in, you observe it. If you see it, then you dive deeper. That's when you start to pinpoint the error. So you start to pinpoint the error. I don't know why uh, it's not loading up. Well, that's weird. my pinpoint error slide is not populated. I'll just kind of chart out what this said. Okay, so in pinpointing the error, just to summarize what these slides said, basically we have collected clues, narrow in on which ones turn out to be the case. For example, e.g., if you saw a null reference, follow that lead. Test again, putting a breakpoint just before it's null. This is just an example. And then you've pinpointed the error. Then you have, if it manifests again, you have pinpointed it. So now we know the exact function. So that's the first step, really. Well, the first broad step is you've now sort of pinpointed that error. And the step 4 is proposing a solution. So that depends on, this one really depends on what's going on with the actual error. How do you prevent that null crash at that point? You can look at similar cases. You can look at similar bits of code and what they've done. Other bits of code that are calling the same function, and they're not crashing. So why aren't they crashing? What are they doing different? You can keep thinking about ways to repair it that may revolve around past behaviors, or you can go into that individual function itself, and perhaps even change the data structure, do whatever is that needed. The one caution there, as we said in the slides, is late in the code we can't change the data structures usually. Late in the process, it's more the further it is in the process of the game being developed, the harder it's going to be to change the underlying structures. Now, ideally, you might want to go back to the original coder to fix this, or at least talk to them. This is a big one here because a lot of times if you were assigned to fix the bug, that implies you should fix the bug. So talking to them might be the best solution there, and seeing how you could actually fix it. Once you've got it, you could just check it in, but that would be the bad thing to do. You want to test it. You also want to test if other bugs were introduced. You could fix something and that could cause 10 other things to break. That's the ripple effect. That's what they're talking about here. So, debugging tips. Question your assumptions. Don't even assume the simple things work. Even sometimes libraries have bugs. Minimize interactions. So try to isolate that bug, meaning if you have to stub in something that bypasses a certain function that you know might be problematic just to find that bug, do it. Minimize the funnel. You should funnel in on the problem without all kinds of extraneous factors. And that's where this minimized randomness comes from as well. Breaking complex calculations into steps. This is where if you've got a big, say you've got a big function that's taking a ton of stuff, you might break that up into, doing multiple mini calculations and seeing if each one is right. Obviously, using the debugger is helpful. checking the code that was most recently changed. That's, again, where you get into perforce and seeing who's done what in perforce. Take a break. This is a big one. It's easy to get too fixated on stuff and think that you have to fix it right away, but sometimes it helps to take a break, debug with a partner, get outside help, that kind of thing. So for debugging prevention, it really helps to understand the underlying system in order to really get to debugging properly. You can add infrastructure such as local game variables on the fly, visual diagnostics, logging data, recording, and playback capability. That allows you to really help your debugging process streamline, make it more streamlined. In Visual Studio, you can set your compiler to high levels of warning and just not ignore warnings, basically. And that could prevent bugs down the road. A lot of games will write their own memory managers that sort of show how much memory is being used and where it's coming from. Using asserts, as I mentioned before, can be another good debugging aid. Avoiding identical code can be something that is very good, so don't do copy and paste all the time. Avoid hard code magic numbers, that makes the system brittle, and verify your coverage. Okay, so that's it for the game development process slides. Normally I'd have a lab today, but I think I'm going to bypass that and not do lab, and we'll just start again with labs. It's kind of hard to have a lab for this stuff because it's very much like process related. So we'll start the labs up again on Tuesday, where I'll see you in class on campus, and we'll be right back at it. I'm going to post this video since we only had one student show up. So yeah, that's about all I got. Stephen, if you got any questions, feel free to type them in. Otherwise, I'm going to close down this session and post it online. All right, see you guys Tuesday.